Good morning. Welcome to the morning session after the conference dinner. We can do this. We've got this. It's my pleasure to introduce Fritz Benedict, who's going to take us through a tale of woe, but hopefully one that either has a happy ending or at least a happy future. So let's hear about astrometry. Thanks, Fritz.
Thank you. Oh, hold your applause to the end. So I didn't come up with this title. Chad came up with this title, and I was on the science organizing committee, and I saw this and said, oh, I want to do that one. I want to do that one. Because in a way, I'm uniquely qualified to answer the question that's on the name tag. Did I really just find an exoplanet? Because I've answered that question probably hundreds of times, and every time in the negative. So it is somewhat of a tale of woe, but if you do astrometry, good things can come of it. So what I want to do is give you an introduction, talk about the early years, and there are in fact some early years in this game. I'm going to talk about one of the shining lights of our history, Van de Kamp and Barnard's star. Then I'm going to talk about HST, because we've actually done real astrometry and gotten real results with HST. Talk about low mass binaries. Everybody's interested in M stars, know your star, know your planet. And then I will talk about the glorious future. All right. So this is the typical response to the word astrometry. But this is about to change, because since April, there have been 109 refereed papers with Gaia in the title. So this is great. I mean, this is wonderful. Gaia, in fact, put me out of business. I won't whine about it too much, but if something's going to put me out of business, I want it to be something really spectacular, and I think Gaia is going to do that. Be spectacular. So mostly what I'm talking about is orbital motion. So we've listen to people talking about how orbital motion will take a planet between us and the star when we get a transit. We listen to people talk about how dragging the star around the planet as it orbits the very center, the star will come towards you and away from you. With astrometry, we get to measure the little circle in the sky. So that's what we're after with astrometry. And this is just a very simple example. And this is what I call narrow field astrometry. Now, Dr. Sozzetti will talk about Gaia after me, and that's a different kind of astrometry. It's still getting the same results, but in narrow field, we're looking at, looking at a science target of some interest and trying to find out if it's moving in an interesting fashion by comparing its position to the position of reference stars in a small field of view. So this is a simple example. There's 5 different observations, different rotation angles, different scales. All those things have to be taken out, so you end up with an overlap solution, and you get residuals to that solution. And if there's something interesting going on, you get to see that relative to your reference frame. All right. So it's not rocket science, but it does turn out to be really tough engineering to pull this off. All right. So 100 years of not finding a planet with astrometry. The real early years, the discovery of Neptune, right? Leverrier, with astrometry, right? So what they were doing basically is looking at Uranus, trying to get the orbit even better than it was before, and notice something funny, that sometimes Uranus seemed to be moving a little faster in its orbit, sometimes it was moving a little more slowly in its orbit. What could be causing this perturbation? Another unseen companion, which turned out to be Neptune. So it should be 172 years of not finding a planet with astrometry, and that's what it'll be from now on. All right. So the next biggie in this game was Peter Van de Kamp. This is a cautionary tale, and Barnard's star. So I'm going to read this to you. This is from June 1944. So remember, this is a long-term project. That's what astrometry is all about. As if to commemorate the 100th anniversary of Bessel's predictions that Sirius has a companion, Peter Van de Kamp, director of Spiral Observatory, has reported new discovery of unseen companions. Two nearby stars have heretofore been considered single, Barnard Star and Lalande 21185, second and third nearest stars to the sun. Okay, so that was in 44. Hey, maybe there's an exoplanet there. June 1969. Now, pointed out an alternative interpretation of the observation. The measured proper motion deviations of our star may result from the perturbation by two unseen companions. So here's an early example of doubling down, right? Which is what the present administration is seemingly excellent at. With approximately coplanar circular orbits with periods of 26 and 12 years. Fantastic. It's not just a single planet orbiting a star, but there's a system, another solar system. And wouldn't that be wonderful? Well, so this was from Sky and Telescope in 1994. I want to draw your attention to this. This is what I wrote on this. What's my hurry, right? Because I'm in the same game, right? I'm in the same business. Here's a cautionary tale. So be very, very careful if you're actually looking for planets around other stars. And in fact, well, in 1995, Phil Ianna came up with this. Investigations at observatories other than Sproul failed to confirm the existence of the perturbation, which it turned out was because they maintained the telescope, which meant taking the lens off, cleaning it, putting it back on again. Is it put back on in exactly the same position? No. What happens? Well, changes how you measure positions of stars. So with this in mind, HST. So this beautiful, beautiful telescope. And here's John Grunsfeld, ass deep in the telescope right here, actually replacing one of the fine guidance sensors, which is the device that we've been using to do astrometry. I have a John Grunsfeld story if someone wants to ask me about it later. It's a good story. But with this, HST lets us measure angles with millisecond of arc precision. That's a quarter 1,500 miles away. That's the angular diameter of a quarter 1,500 miles away. If you don't know what a quarter looks like, I hardly, any kind of change I get, I donate to charity, obviously. I like this picture too because it's that boldly go into, oops, wrong way, boldly go into space. But it also shows this, which is the docking ring that they're going to use to deorbit burn Hubble Space Telescope someday, so you don't have an 800-pound frisbee slice through Chicago. It'll get deorbited into the Pacific Ocean, and with any luck at all, be sitting in a hot tub on a cruise ship, drinking a margarita, watching it come back in, and that will be the capstone of my career. All right, so here's the focal plane of Hubble, and this is what we used. We actually used FTS-3 for a great many years, but then as soon as they got a better one up there, we used the better one. Most of the results I'll talk about use this better one. And what are we doing with it? What we're doing with it, the fine guidance sensor is basically an interferometer. To us, Hubble is an interferometer with a baseline of 2.4 meters. What we've got is what's called a Kester's prism, and basically it's a wavefront tilt sensor. So the wavefront's a little tilted, you get a little more light off of one side than the other, so you put a phototube here, a phototube there, depending on the tilt of the wavefront, which means the position that the object is in. If you're looking, you get a different signal out. You take those signals and do a really terrifically difficult arithmetic, and you end up forming a fringe, and you can measure the zero crossing of that fringe, and voila, you have a position. And what we do is, go back, is we basically march around the fine guidance. So we have an interesting target here, and then we have reference stars here, here, and here, and we march around in serial fashion and derive position. All right. So what did I want to do with this? So starting in 19 77, late 77s, when I first got on the astrometry science team for Hubble Space Telescope, and we said, well, what are we going to do with this? At that time, we were hoping to get 2 to 3 milliarc-second precision out of the fine guidance sensor. And even in those early days, having read an immense amount of science fiction, I was inordinately interested in whether or not there were planets around other stars. And so that's what I wanted to do with it. And each of the team members got a certain number of orbits. And I augmented my meager number of orbits because I was in charge of the science verification for the FGS. And so, gee, science verification, I just need to measure a bunch of stars and in a number of different times, make sure that the stability of the instrument was good, that it was going to actually do millisecond of arc astrometry, blah, blah, blah. And so what fields did I choose? Well, it just happened to have Proxima Cen in it, right? So I didn't just burn a large number of orbits. So observation sets, that means orbits with Hubble Space Telescope. That's how they meter it out. So if you get orbits, you get 5 orbits. If you're excited, you can do some science. Not with astrometry, though. You've got to have at least 10 to 12. But got lots and lots of orbits, and over 5.6 years. And with Barnard Star, a little less time. And that's what we burned. That's what I burned. So with the science verification plus the guaranteed time observation, and even a little guest observing time that I got, we got a series of measurements of the position of Proxima Cen relative to a reference frame of about 8 stars. It's in a nice rich field. And what we're trying to do is look for a perturbation, look for some sort of a rhythmic change in the position of that object. And well, here's the example of Barnard Star. And it demonstrates a couple of nuisance parameters that you have to remove. You have to remove the proper motion, the thing is zipping across the sky, and there's a parallax. So those you got to remove with considerable precision, and then the residuals to that are what you inspect to try to find something that's wiggling around that could be ascribed to an orbiting planet perturbing the star. So can't read this, but these are 2 signs that I have up in my office. And for many years, for with slight effort, how should one obtain great results? It is foolish even to desire it. That was Euripides. And then Richard Feynman, the first principle is you must not fool yourself, and you're the easiest person to fool. I was really keen to walk over across the way and see all that stuff about Richard Feynman, since he's been a guiding light in my life for many years. All right. So did we do a good job? Yeah, we did a good job. So here's the residuals to the fit for Proxima Cen. And basically, in one axis, we're doing better than a milliarc second. In the other axis, we're doing a milliarc second. And the residuals are reasonably Gaussian. So is there a planet hiding in there? Then the short answer is no. There's no planet hiding in there. And this was the result. And this is, again, ancient history. 20 years, I can hardly believe it. It's 20 years ago. Actually, 19. In 1999, this came out. So basically, I could convince myself as the data dribbles in and you continually analyze it. And 1 week, oh, God, there's a planet there. There's a planet. Oh, this is very exciting. And then the next week, a couple more observation sets come in and it goes away, right? Very frustrating. But finally, with Monte Carlo simulations, we've managed to convince ourselves that a 1 mass amplitude perturbation would be found at a 1% false positive level with a 5% miss rate. So basically, this is companion period in days. Here it is in astronomical units around Proxima Cen. This was the radial velocity limit as of 1999. And this was our astrometric limit. So basically, if there was a Jupiter mass planet orbiting Proxima with a period of 40 days, we'd have seen it. If there was a Saturn mass planet orbiting Proxima with a 400-day period, we would have seen it. But there's not. And I'm very happy with that result now because nobody's found anything of that mass around Proxima Centauri. Think of the embarrassment if we'd have said, oh, look, there's a Jupiter mass planet. You know, back then we didn't know an M dwarf could have a Jupiter mass planet. Why not? Well, now we know, no way. All right, we did miss this one, right? There's no shame. That's at this period here, about 11 days. And on this scale, so there's a tenth of a Jupiter. On this scale, it's down in the basement someplace. Would have required 1 microsecond of arc precision, not 1 millisecond of arc precision, which we couldn't do. All right. Oh, here's yes. There's a bottle of Springbank 25. Why do I show this? Well, in 1994, there was an IAU meeting in The Hague. It was a great meeting, and I gave an interim report about our search for planets around Proxima Centauri and Barnard Star. And fortunately, I flew back through Heathrow. And back in 1994, Heathrow had the wonderland of Scotch, right? They had a store, and there was every Scotch known to man or God. And so I bought a bottle of this Springbank 25. Why? Because either I was going to find a planet and I would celebrate, or I didn't find a planet and I would need the Scotch, right? So it ended up I needed the Scotch. I may come back to this. Somebody remind me when I talk at the very end to talk about this again. But so you look online now. I mean, you can Google this stuff. It's fantastic. Tasting notes, nose, palate, finish, all this stuff. You know, and I drink it. I say, that's good Scotch. I can't taste any of that stuff. Who can? But I draw your attention to this last part here in the finish. The soft burning embers, the dregs of my hopes having gone up in flames. All right. So we didn't find a planet, but we haven't failed because we've done lots of more interesting, equally interesting things. If somebody can tell us there's a planet there, my radial velocity friends, then perhaps we can go and measure the perturbation. And if we can measure the perturbation, then you don't have that stupid M sin I ambiguity. You have the mass. So what we've done is done this for a number of objects, and we've gotten a number of masses, right? And they're all Jupiter kind of masses, which is fine, great, we've done that. That made me very, very happy. Now, if you could rise above the solar system, say 10 parsecs away, and were very patient and had a very good astrometer. An astrometer is the instrument, an astrometrist is the person who does it. And you waited 50 years, so you would want a robotic astrometrist because you wouldn't want to sit out there for 50 years. And you watch the motion of the sun. So starting in 1960 to 2025. And this is what the motion of the sun would do. And why? Because Jupiter and Saturn are dragging the sun around. Neptune and Uranus a little bit. The amplitude of the Earth drag is smaller than the width of the line here, right? But still, it's an interesting plot. And what I was burning with desire to do is produce a plot like this for a different system. And we did this for Hubble and Andromeda. Barbara MacArthur did the work on this. But I made the plot. And so here's our plot for Hubble and Andromeda. And in fact, there's a nice curly Q because there's two things there. There's two planets. And if you had sharp eyes, you could tell one was 9 Jupiter masses, the other one was about 11 Jupiter masses on the table. All right, well, that's pretty cool. But that's looking down, right? So what happens if you look from the side? Is it like our solar system? And oh, and here's a quarter. That's what our precision was. That's 1 milliarc second right there. So we're doing pretty well. So the Hubble and Andromeda system is not so much like ours, right? So somehow, and I'll show you in the movie, it, in quotes, screwed up the system because it's not coplanar. And you could tell it's not coplanar not from radial velocities, but from the astrometry. So this movie, and you have to ignore the hot Jupiter, right? So there's a hot Jupiter. Did the migration of the hot Jupiter screw up the system? There's a cottage industry of dynamicists writing papers about this now. So here's what we found. So there's this movie. So you have to ignore the inclination of the hot Jupiter, because we had no idea what the inclination of the hot Jupiter is. But this was just demonstrating that it was non-coplanar. Look at that. See, there's mutual inclination of about 30 degrees, which was a huge surprise, since we just naively assumed that all solar systems would have the architecture that ours does. That was wrong. So the other thing is that Andromeda has a distant companion, this red dwarf, about 10,000 AU away. We have no idea what the orbit is. Maybe Gaia will tell us what the orbit is. It's highly elliptical, in which case it could have something to do with the odd architecture of the system. All right, here's another system that we worked on, and that unfortunately blocks the telephone number for it, the HD 202206. And it turned out to be, and this is great, this is what, if you ever want to motivate somebody else, put a question mark in your title, right? Or in the result. So some radial velocity people, gee, is this a brown dwarf? It's what is it? What's going on? And so threw the gauntlet down, and the astrometry could answer it. Turns out that one of them is a star that's supposed to be a sun symbol, and the other one is a brown dwarf. And there's a spaghetti diagram for that. And this one, though, it turns out to be nicely coplanar. So coplanar and, 5-to-1 resonance, or very close to it. All right. So one important aspect in all of this work is to look at the long periods of most of these things. And astrometry, until the age of Gaia, you're not rich in it, right? And if you're asking for orbits with Hubble Space Telescope, that each epoch of your measurement is an orbit, people are really stingy with that stuff, and they will lose patience with you after 2 or 3 years. And these things have long periods. So what helps us out? Radial velocities help us out. So astrometry is scarce, but discovery and follow-up RV can be very rich. And through this lovely equation here, you can relate all the astrometry to anything that you can derive through the radial velocities. And it essentially phases the astrometric observations so that you can back out the amplitudes of the perturbations and get the masses. All right, so 172 years, no findings. But astrometry can assist the exoplanet game in other ways. Low mass binaries in the lower main sequence mass luminosity relations. So know your star, know your planet. M dwarf stars, hot, they're cool, but hot targets for JWST. There was an article in the Washington Post this morning that you wonder, nuts and bolts falling off the thing. One hopes that it will not be the telescope that ate astronomy. They said that about Hubble Space Telescope as well, so shouldn't worry about that too much. So what about so basically with the fine guidance sensor, we studied, I think, 14, 16 different M-dwarf binary systems, measured the orbits, separations and position angles, got a mass fraction, which means that we could relate the primary star to a reference frame, and with that, derive masses for a number of stars. And in this example of GJ831AB, so 0.27 and 0.145 mean mass error of about 1.5%. And doing that for 14 to 16 systems, you can build up a very nice mass. Oh, I shouldn't even do this. This is an embarrassment to even show this plot in a group that does meter per second RVs. So here, oh, damn it. So that's 5 kilometers a second, and those are my error bars. But still, it in fact helps inform the masses of this system, because you're sampling a process that's going on both astrometrically and with radial velocities. and it improves the accuracy of your masses. All right, so again, you got to have this constraint. That helps. And the end result is this lovely gas-luminosity relationship that we published in late 2016. I worked with Todd Henry on this, and we went through 15 versions of the paper. I submitted it on a Friday. It was accepted on a Monday. So the rule here is the more you bleed on the practice field, the less you bleed in battle, right? So here's our mass luminosity relationship. So hey, if you can measure a K band or even a V band, because we've got a V band, one of these two, if you can measure a K band absolute magnitude, you have to know the distance. Guy's going to tell you the distance. Then you can go in here and find out what the mass of your home star is. All right. Oh, where do we get the delta K? Hey, we used the high resolution, high contrast imaging stuff as well. So here's Serge Dietrich, and he did his thesis helping to come up with nice delta K magnitudes and K magnitudes for the component. All righty. The glorious future. All right. This was going to find Earth mass planets in 1 year orbits orbiting, 1 year periods orbiting G-type stars. It's dead, all right? Not going to happen. Not going to happen. All right. I won't whine too much about that, except I'm still pissed. All right, and this was a sales plot, all right, but it's a good plot to show because Dr. Sozzetti may discuss this a little bit. So here's Gaia. We were always, everybody in the astrometry game, you're always competing with Gaia. So you always have to have your obligatory, this is how much better we would do than Gaia, or we'll do just as well with Gaia. And so here's Gaia demonstrating that it can do Jupiters. And one hopes they will find thousands of Jupiters. And better than that, hundreds of systems where you can test whether or not they're coplanar or not. SIM, on the other hand, was going to find Earth-like planets around the brighter stars. Well, that's not going to happen, is it? All right, so he's up next. This isn't going to happen. So, and about Gaia. Gaia passes my test, right? You say, well, there's a billion stars, of, huge number of parallaxes. Can you trust those parallaxes? So the one group that's done fairly decent parallaxes is my group, and with the Hubble Space Telescope. And so here are HST parallaxes in milli-arc second, and this is a log scale versus Gaia's DR2 parallaxes in milli-arc second, a log scale. There's the regression line. These are the residuals. And you'll notice something that there are some things that fall off. And it turns out that for a Gaia magnitude less than about 12, they have some problems. So these are in particular Cepheid variable stars. So be careful. If you've got a bright target, you might want to wait for DR3 because they'll probably clean up some of this stuff. All right. Back to this. So next. So when is astrometry going to find us an Earth-like planet, right? When is that going to happen? So what's Theia? Theia is an astrometric space mission, and they're selling this based on the fact that they're going to get super Earth and Earths with masses greater than 1.5 can be detected and characterized around 22 stars. All super Earths with masses greater than 2.2 can be detected and characterized around 59 stars. So you say, wow, you can find 80, 81 Earths, but they're not one, they're more than that. So how are you going to sell this? Well, and here's the plot that they use, which is here's a mass detection limit in the habitable zone versus system rank, and some of your favorites are here. Here's alpha Cent A and B, here's Proxima Cent, some other things. So they think that they got a good shot at this. All right, they got a good shot, but based on this, you don't sell this mission, right? So you've got other things. Dark matter. This is going to measure the motions of stars around satellite galaxies. It's going to be able to map the small scales of dark matter, things like that. That gets everybody a little more excited than just the people who are interested in exoplanets. All right, how are they going to do it? Basically, monitor. They have an optical truss, and then they keep the optical truss absolutely stable by laser interferometry. So it's like LIGO in space, but all they're interested in doing is keeping all the mirrors in the right position all the time, right? Now, is this going to happen? We should find out in December, because basically, ESA is the prime putting it together contractor. They don't have any money yet. Japan is really interested in doing this, and if they decide to spend the money, then this will go forward. All right. In the near term, there's this, which I'm so happy to be a part of. Right here I am, the junior member. We proposed a pilot study consisting of a series of high signal to noise observations in the nearby stellar binary alpha Cent A and B to make precise measurements of their relative orbit. That's a nuisance, right? They're going around each other. If you're interested in a small perturbation due to a planet, you got to remove that orbit first. So, in addition to probing the limits of ALMA's differential astrometric position, these measurements will improve our knowledge of the orbit, blah, blah, blah. So, this was put in. I am happy to report, as of yesterday morning at 10:30 a.m., we got the time. So, this is going to happen. And I'm even happier that there's a whole bunch of people on this that know a whole lot about interferometry at ALMA, because I know nothing about interferometry at ALMA, but I do know how to do some astrometry with the end result. So that's going to be great fun. Now, when I told my wife that, hey, these people are interested in having me work on this stuff, this was her reaction. So here's Alpha Cent, here's me, and there's my wife. You really going to tilt at the windmills again? I said, I do so enjoy tilting at windmills. So you got to be really into process if you're an astrometrist, right? Okay. So, summary. Astrometry has yet to independently discover an exoplanet. This is about to change, I hope. Astrometry has made useful contributions: exoplanet masses, system architecture, host star characterization. The future is seemingly bright, although true Earth analogs are just out of reach, right? Even Thea is weaseling on that. I mean, is it 1? No, it's 1.5. So is it like fusion power, always a few years off into the future? And I'll leave you with this. This is back to basics, support astrometry. Here's the astrometrist. There's spectroscopists, atmospheres, interiors, cosmologists, general relativists, cranks, and other fuzzy-brained pencil pushers are up at the top. So with that, I'll leave you a nice picture of the grand team. Thank you very much.
All right, questions for Fritz? He set up several through the talk.
Excuse me? I did, yes, very quickly, actually. Yes. Oh, the Scotch bottle, I need to buy another one, because I checked online. It's now $750 a bottle for Springbank 25. So I'm going to have to lower my reward for Alpha Cent, and have to live long enough too. There's a couple of multi-planet systems,
that had dynamical masses determined by the radial velocity data themselves, and they came out with much lower masses, therefore more edge on orbits than you got. So I wonder if you want to address that.
No. No, we basically, with the equipment that we had, we did the best job we could do, and that was the result we got. So can I explain the difference? I cannot explain the difference.
Underestimates the error bars?
Could have. Yes, if I increase my error bars a whole lot.
Or if they increase theirs.
Yes.
So what's your suggestion to young PhD students working on astrometry with Gaia program?
Yes, the question is, do I have any words of wisdom for a young astronomer doing astrometry with Gaia? So, you may wonder, why the hell am I wearing a tie, right? This is the only tie you've seen this entire workshop, right? Well, I'm old school, and as I have done astrometry for 40 years on soft money. And one of the ways you do that is to be very good at what you do. The other thing to do is you're basically a company with one employee. So represent, right? Get up, dress up, go to work, right? So that's one thing. The other thing is pick a really good topic, right? Gaia's already there. I was really lucky with HST, and it was a long, strange trip. First astrometry I did was a thing called a PDS machine, a photometric data systems plate scanner, right? Turned out the guide star selection system, which I did not build, but I designed it, right? I told them how to do it, and so that was my job for the first 3 or 4 years. The other thing is, don't get really in love with any one project. Be willing to, there's a video game, which is probably too old that most of you haven't even ever seen it, called Frogger, right? Where you jump from log to log to log. That's what your career is going to be like, unless you're extremely lucky and get tenure when you're 25 years old, right? You're going to jump from log to log and hope the alligators don't eat you. So none of this is very useful to you, but the most important thing is to have fun while you're doing it, because as long as you're having fun, it's okay. So if you get stuck in something, you say, this is crap, I'm not going to do this. Don't do it, right? Find something else to do. Honestly, as graduate students in astronomy, you can do anything. And it's sad if you get your PhD and you don't get to do astronomy, especially astrometry. But go out, make your millions of dollars, retire early, and do astronomy. I know several people who have done that, right? You're just delaying the inevitable doing of astronomy. You tell my John Grunsfeld story. All right, so Grunsfeld went up to Hubble 4 times, and at least 2 of the times he replaced the fine guidance sensor so he made sure that I could still do my science right. So to me, he's a personal hero. He's very brave to go up there. He's very good at what he does. So in 2009, just before the last servicing mission, he was going to go up again, right? And there was a AAS meeting in Long Beach, and I knew he was going to be there. I make every effort to go and shake this man's hand because he's my hero, right? And he's fixed the telescope. I would be out of a job unless he was there. So I walk down the hall. Who do I see coming for me? John Grunsfeld. Dr. Grunsfeld, I'm so happy to meet you. I just want to shake your hand and thank you. And I'm reaching for his hand and I'm thinking to myself, oh, he's an astronaut. Those gloves that they wear, he's got to have a grip like steel, right? Because he's got to move those. God, I better squeeze hard. And I think, what if I squeeze hard and break his finger? And then he couldn't go up, And so what ensued was the weakest limp fish handshake in the history of two men meeting each other for the first time. I didn't break his hand. And after the servicing mission, I got to see him again. We had a nice manly handshake. So have fun with it. That's so important. Really. All right, thank you.